Give me your materials before the break. What you owe me is lesson 7, lesson 8, lesson 9, quiz 3, exam 3, and lab 3. So the last lab we did, which was the last time we met before break, was lab 4. And so lab 4 is not going to be due for another month. Well, actually, right now I'm going to get this door closed. But I will send you the videos now for Lab 4 so that you can go through the process of determining the velocity before and after the collisions and test out the elastic and inelastic collisions. Again, I didn't want to send those to you over the break because I didn't want you to have to worry about them as though Lab 4 was due when we came back. The lab that's due now is Lab 3, which I can't remember exactly what we did in Lab 3. Oh, the spinning, yeah. So, all right. Any questions about what's due, what you owe me? All right, cool. So the nice thing about lesson 10 is it picks up right where we left off with lesson 9. Lesson 9, we talked about the first law of thermodynamics, and we talked about that the total energy of the system is equal to the heat absorbed by the system minus the work done by the system, right? And so we're going to continue to talk about this first law of thermodynamics, but to spend some time talking about, well, how do we know how much heat got absorbed? What does that actually look like? And then how do we take that to figure out how much work can be done? So as we work in that direction, our first question that we're going to address is this: what is energy? And we've had this question before, actually a couple of times. And it's nice to just always go back to our definition of energy so that we can just kind of continue to connect concepts. So remember that energy is defined as the capacity to do work. So energy is defined as the capacity to do work. No matter what type of energy it is, if it's kinetic energy, energy of motion, or if it's potential energy, right? Energy associated with position, or if it's chemical energy or heat energy, it's all the potential to do work, to take some force and execute that force over a particular distance, right? There's a potential to do this. And this is why a lot of the times in physics, even when we're dealing with like thermodynamics, we set up a system in which you're just kind of moving an object over a distance so you can visualize what that energy is actually doing. Because it's hard to visualize the energy in a candy bar, right? I mean, you can think about it and you're like, sure, like if I'm hangry and I eat a candy bar, I'm not hangry anymore, right? Because I got that energy. But it's hard to actually visualize. Come on in. There's room up here, and then, it's fine. I'll have Malachi move back, and then y'all can sit up here. Yep, you are very welcome. Now I feel bad. Okay, so next week, those in the back, you're gonna have to move up so we can leave some space for Malachi and Isaiah's family. Also remember that energy comes in many forms. And so we've even seen this. We've seen kinetic energy, we've seen potential energy, we've seen heat energy, right? Heat absorbed, that Q that we saw when we first talked about the first law of thermodynamics. Now, kinetic energy, it's very obvious how that is used to do work, right? Last thing we saw, we had like problems where we had a car with a particular amount of momentum. And we talked about, okay, what if all of that momentum was transferred into moving this, 430 Newton block, a certain distance, right? That's our homework problems from lesson 9. And so it's very obvious to see that, right? You take a car that's moving a particular speed, you ram an object, you're like, yeah, it's doing work. It's obvious. But heat energy can also be used to do work. This one is not, again, it's not as obvious. You think about heat energy when, you step on, the concrete around a swimming pool, Like you get out of a swimming pool and you feel fantastic, and then you step on the concrete and you no longer feel fantastic, right? feels awful because that heat energy transfers from the concrete into your foot, right? And so you know heat energy, you've felt it, you've experienced it, but you may not oftentimes think about that heat energy being used to do work. But this is what happens in engines. In engines, we harness that heat energy. We burn gasoline and use that energy to power, the moving of tires and to move an automobile. We actually had at least 2 people in here get their permits over the break. Did either of you get your permit over the break? You did? Nice. So we have 3 people got their permits to operate an automobile over the break. And so now you can think about this whenever you're driving. Don't think too much about it because you want to think about what you're supposed to be doing safety-wise while you're driving. But yeah, I mean, in engines, we harness that heat energy to do work, to actually convert that into kinetic energy. Now, it is more difficult to harness than kinetic energy, and so a lot of it gets wasted. A lot of our heat energy gets wasted, but for simplicity's sake and in the problems we deal with, we're going to assume 100% efficiency. We're going to assume if we absorb this amount of heat energy, we're going to be able to convert all of that into doing work. Okay? In reality, that's not what happens, right? Have you ever felt the hood of a car after it's been running and it's warm? And what that means is some of the heat energy generated by burning the gasoline went into making the hood warm, which doesn't help you move, right? That's wasted. It's wasted energy. Okay. So yeah, I mean, engines aren't 100% efficient, but we're going to assume for simplicity's sake today that they are. Okay. If you have problems with that, I can go in and plug in and give you an actual efficiency and say, okay, well, this engine is 30% efficient. So 30% of the heat energy can actually be converted into doing work. 70% is just lost as heat. If that's what you want, we can make that happen. All right? And so here is the formula that we're going to use, because we saw Q last time. And I know it was 6 weeks ago. It was a really long time. But we saw Q, which was heat absorbed by the system. Well, that's nice, but unless we can actually measure that, it doesn't really mean anything. And so the way we measure this is actually by a change in temperature. And so we have this formula for Q. Q is that heat energy, the heat absorbed by the system. And so that heat energy is equal to the mass of whatever that material is, times the specific heat of that material, which we'll talk in the very next slide about what that is, times the change in temperature. And now we have something we can actually measure. Right? Have any of you measured the temperature of something? Cool. Should be everybody. You've either directly measured it or at least read the measurement of the temperature of the air, right? So that's something we're familiar with, right? We change in temperature. If it changes from 45 degrees when you wake up in the morning to 70 degrees at 2 o'clock in the afternoon, you know exactly what that feels like because you experienced it today. Right? It didn't actually get quite up to 70. I think it's 65. But you experience that, right? A change in 20 degrees Fahrenheit. Like, that's something that's meaningful. Me telling you 57 joules of heat energy, that doesn't mean anything. I mean, it means something, but it's not tangible. So specific heat, and you'll see this when you see the units of it, but specific heat is the amount of energy required to heat a certain amount of the object, to get a certain change in temperature. So we usually present the units of C, the units as joules per grams degrees Celsius. So joules, the amount of energy required to heat 1 gram, 1 degree Celsius. Okay? Does that make sense? So these are our units for C. I don't have that listed on this slide. On the very next slide, we have our first practice problem that we'll do together, and I'll actually give you the specific heat of the object. All right? So this is what specific heat is. It's the amount of energy required to heat 1 gram of it, 1 degree Celsius. And unfortunately, we have to, maybe unfortunately, maybe it's fortunate, we use degrees Celsius. Even though, we use degrees Fahrenheit. Now, does anybody want to take a guess as to which material on Earth has the highest specific heat? And I'll tell you, it's not even close. There's nothing that even comes close to this material. Highest specific heat. So the highest specific heat means that it's going to take the most energy to heat 1 gram of it 1 degree Celsius, more than anything else on Earth. And it's not even close. What is the ocean made of? Water. Water has by far the highest specific heat of any material on Earth. Not even close. Which means of all materials on Earth, water does the best job resisting temperature change. Right? You include it into the ocean. There's a big giant pool of it, right? Yeah. It's cool. It's cool stuff. We'll talk about some of the implications of that someday. How much heat is required to raise the temperature of 5 liters of water 5 degrees Celsius? And that's for this, our specific heat of water is 4.184 joules per grams degree Celsius, and every 1 milliliter of water is 1 gram. All right? So here's our problem. The reason why I use 5 liters of water is you all have probably had a liter, soda or a liter of water at some point in your life, or you've seen a 2-liter bottle of soda. So 5 liters, even though you don't typically measure volume in liters in your life, it's a volume that you should be able to visualize roughly quickly. All right. So how much heat is required to raise the temperature of 5 liters of water 5 degrees Celsius? All right, so what do we have, or what are we given by this problem? We're given the specific heat, right? The specific heat of water is 4.184 joules per grams degree Celsius. So it takes a little bit over 4 joules of energy to heat 1 gram of water 1 degree Celsius. We also have the mass of water. And you look at this and you may not see the mass right away, but we have the mass because it tells us that we have 5 liters of water. So we have the mass is equal to 5 liters times a certain conversion factor. So first of all, the mass is equal to 5 liters times how many milliliters are in 1 liter? Remember our 1,000. 1,000, right? Remember these prefixes? So our mass is equal to 5 liters of water times 1,000 milliliters per liter, yes? And then times 1 gram per milliliter. You see that? All right, so now milliliters is on the bottom here, right? So that means if it's on the bottom here and the top here, we can cancel it, right? If we're multiplying milliliters and we're dividing milliliters, they cancel out. They equal 1. Same thing here. If we're multiplying liters and we're dividing liters, they're going to cancel out, right? They equal 1. And so what would we be left with unit-wise? Just grams, which is excellent because I told you we were given the mass of water. And how do we measure mass? In grams. Or kilograms, but in this case, grams. Is this okay? You okay, Josh? All right, so then we do 5 times 1,000 is what? 5,000 times 1 is 5,000. So the mass of this water is equal to 5,000 grams. And I know it wasn't super clear that this problem was giving us the mass of water, but from now on, if you're ever given the volume of water, you can always find the mass because water is always 1 gram per milliliter, which was given here. 1 milliliter of water is 1 gram. 1 gram per milliliter. Okay? We'll do this time and time and time again, and so you'll get very used to taking volume of water and going into mass. If it's a little weird right now, we're going to do it pretty much every problem we deal with water. Okay, unless they gave us specifically the mass of water. Okay, so it gave us a specific heat. It gave us mass. Now we start thinking about any tools that we have. Oh, it also gave us change in temperature. I didn't realize that, and nobody said anything. What's the change in temperature? 5 degrees Celsius. So it also gave us our change in temperature, our delta T is equal to 5 degrees Celsius. Okay. Now tools. What tools do we have that contain specific heat, mass, and change in temperature? It's okay to answer this. Yep. Q equals MC delta T. All right? Now, what is this problem asking for? What do we want? We want Q, right? We want to know how much heat energy is required to do this. So Q, our tool is already set up to solve for Q. Q is equal to our mass, which is 5,000 grams, times our specific heat, which is 4.184 joules per grams degrees Celsius, times our change in temperature, which is 5 degrees Celsius. Right? Now, unit-wise, here we've got degrees Celsius being divided away. Yes? Here we have degrees Celsius being multiplied. So what happens to them? They cancel out. Oh, this one doesn't work at all. Garbage. Okay, here we have grams divided away. Here we have grams multiplied. What happens to them? They cancel out. And for units, we'll be left with joules. Why is that nice? What do we measure energy in? Joules. So again, our units canceled. It is an indication that we set up our tool correctly. Right? Because what we want should be measured in joules, and the units we have left are joules. So we have 5,000 times 4.184 times 4.184 times 5 degrees Celsius. Okay, this has how many significant figures? 1. So our answer can only have 1. And so we have 100,000 joules. It requires 100,000 joules of energy to heat 5 liters of water, which isn't much, right? 5 1-liter bottles, 5 degrees Celsius. That's a huge amount of energy compared to what some of the things we were dealing with kinetic energy, right? That's a huge amount of energy, which is why water does such a wonderful job keeping the temperature from fluctuating very much. Any questions? We're going to do this again. Very next problem deals with water again. So how much heat is required to raise the temperature of 125,000 liters of water 5 degrees Celsius? Can you all see this board right here? Colby, can you see right here? Okay. So what do we have in this problem? We have the same specific heat, right? It's still water. It gave it to us again in case we were wondering if we would use the same one, but it's just water. So joules per grams degrees Celsius. We have the same change in temperature, which equals 5 degrees Celsius. But now we have a different mass. But does this problem still give us mass? You better believe it does. because it gives us that the mass is equal to 125,000 liters times how many milliliters are in a liter? 1,000. 1,000 milliliters in 1 liter times how many grams are in 1 milliliter? 1. 1 gram per milliliter. So just like we did there, we can use what we're given to solve for the mass of water. So if we divide milliliters away and we multiply it, what do we do with them?
Cancel.
We cancel. So you can see this, Colby?
Kind of the glare from the screen.
From this screen or from the light?
From the TV screen.
Oh. Let's do this. Is that better? Is that better, Colby?
Yeah.
Okay. And so here we have liters being multiplied. Here we have liters being divided away. So those can cancel as well. And then we're left with grams, which is nice. Because what should mass be illustrated in? In grams. So 125,000 times 1,000 is 125 million. Times 1, so we have 125 million grams of water. Do you know why I use this volume here? This is the volume of the average swimming pool, 125,000 liters. Water purifier, dripping water. Can't handle it. All right, tools. What tools do we have? Same tool we used here, right? Q is equal to MC delta T. All right? And then what do we want? What do we want to solve for? Still Q, right? We want to know how much energy. So Q is equal to our mass, which is 125 million grams. Whoa, sorry. 125 million grams times our specific heat, which is 4.184 joules per grams degrees Celsius, times our change in temperature, which is 5 degrees Celsius. And just like before, anything that's being multiplied and being divided away will cancel out. So degrees Celsius will cancel out, grams will cancel out, and we'll be left with what, unit-wise? Joules. And then now we'll do 125 million times 4.184 times 5 degrees Celsius. And notice this only has one significant figure, meaning we need to present our answer to one significant figure. And we have 3 billion joules. That is way more than anything we've seen before, right? I mean, we had things like 30,000 joules, and we were like, wow, that's big. 3 billion joules to heat a swimming pool 5 degrees Celsius, which is about 10 degrees Fahrenheit. So you're like, you know what? I really want to go swimming, but it's March, and my pool is 65 degrees. I'd like for it to be 75 degrees. It's going to take you about 3 billion joules of energy to make that happen. No big deal, right? No big deal. Is this okay? Okay, cool. All right, so now the question is, well, how does this impact work? Because, I mean, this heat energy, you're like, that's cool, you know? heat energy, we're solving for Q using a change in temperature, something that does make sense. I can understand change in temperature because I felt objects change, temperature before. And you're like, yeah, it's really cool, but we talk about energy being the capacity to do work. So what does this mean? How do we actually use this to do work? I'm glad you asked. So remember that we said that heat energy can be harnessed. We can harness heat energy. And we can use that heat energy to do work. Now, we also mentioned that it is more difficult to harness heat energy than kinetic, right? As the kinetic energy of like a child is pretty difficult to harness unless you put them on a wheel, a wheel that's attached to some kind of a turbine, so it can spin something. That'd be great, man. I ought to do something like that because my son is just, he's crazy. Sometimes we have to just send him in the backyard to go like run around and jump on the trampoline so he stops biting his sisters. So, if we could harness some of that energy, that'd be good. So, if the total energy of the system remains constant, which is what we're going to assume for simplicity's sake, then all of the heat absorbed by that system can be converted into work. And again, I told you we're going to assume things for simplicity's sake that aren't necessarily true. But it keeps it simple. So we're going to assume that the total energy of the system or of all of our systems remain constant. And so any heat absorbed by the system can be converted into work done by the system. So if you remember back to our formula, U, or the total energy of the system, is equal to heat absorbed minus work done by the system, right? You remember this formula? Even if you don't, you can nod and say you do, because you remember it a little bit, even if you can't think of all the details. It's somewhere in your brain. It's there, whether you want it there or not. I learned that this very week, actually. I had to cover organic chem labs, and I haven't done an organic chemistry lab in 11 years. And I walked in there, and as soon as I smelled the lab and what the students were doing, it all came back to me. And I remembered all the wonderful, wonderful time I had in the chemistry lab trying to figure out what I had. And by wonderful, I mean terrible. And by terrible, I mean the worst experience of my college life. But it's all right. Those are stories for another time. So what we're going to do is, just for simplicity's sake, we're going to say that Q is equal to W. Any heat absorbed by the system is going to equal the amount of work that the system can do. Okay? This is what we're going to say for simplicity's sake. And since we just, got a new toy today for calculating Q, we can say this, that MC delta T is equal to work. MC delta T is equal to work. Now this is cool, because now we can do something completely different while doing something exactly the same, right? All we're doing is calculating work in the same way we calculated Q. So we're doing something different, and that is determining how much work can be done while doing something exactly the same, using the same tool. It's fantastic. Wonderful things that you can do when you say, for simplicity's sake, we're going to harness all of this heat energy and do work with it. All right? So here's our question. How much work can be done by a 3.50 kilogram piece of metal that increases 56.5 degrees Celsius if the specific heat of the metal is 1.35 joules per grams degree Celsius? This is a good one. This is a good one. All right, so what do we have? What do we have? What are we given?
Mass.
We are given mass. Mass is equal to, ooh, this marker looks nice, 3.50 kilograms. Okay, what else are we given? right? We're given specific heat. What is it?
1.35.
1.35 joules per grams degrees Celsius. And we're also given what else? Change in temperature. How much does the metal change in temperature? 56.5 degrees Celsius. Are you all afraid that you're going to say something that's not true? Is that why some of you don't answer? Or are you just afraid we might not like the way your voice sounds? I'll like the way your voice sounds. Welcome back, by the way. Did I welcome you back? I'm so happy you're back. I'm so back. I'm so glad we're here together. You know? I don't get to do physics all the time, so this is fun. All right. So this mass is cool, but we've got a bit of a problem. In that the mass in our specific heat is measured in what? Yeah, the mass here is measured in kilograms, but in our specific heat formula, or in the units of our specific heat, it's in grams. So we want to put this into grams. So you're like, okay, the mass is 3.50 kilograms. How many grams is that? How many grams are in 1 kilogram? What does that root kilo mean? Yeah, kilo means 1,000. So there are 1,000 grams in every 1 kilogram. So if we multiply 3.50 kilograms by 1,000 grams per kilogram, because there are 1,000 grams in every 1 kilogram. So we're multiplying kilograms here, we're dividing it here, we can cancel those out. And we get 3,500 grams. Now, the thing you have to notice is here we only have 2 significant figures, but what we were given had 3. So we're not going to limit our answer to 2 because we know it was exactly 3.50 kilograms. Okay, just keep that in mind because this is something we did in the middle of a problem. It wasn't what we were given. And there are exactly 1,000 grams in a kilogram. That's what kilogram means. All right? Now, what tools do we have? We manipulated our tool so that it wasn't Q equals MC delta T. What was it? W. Work equals MC delta T. And we did this by assuming that all of our heat energy could actually be put into doing work. So you see this? We're doing something different, calculating work, while using the exact same tool. How neat is that? It's pretty neat. Have you seen that, the Nature Show? No. Okay. All right. So what do we want? What is this problem asking us to calculate? Work. And our tool is already set up to calculate work. Work is equal to 3,500 grams times 1.35 joules per grams degrees Celsius times our change in temperature, which is 56.5 degrees Celsius. That okay? Remember, we're doing something different while doing the exact same thing. Grams is multiplied here, divided away here, so it can cancel. Degrees Celsius is multiplied or divided away here and multiplied here. Those cancel each other out. And so we have 3,500 times 1.35 times 56.5 equals, and remember this is not going to limit our number of significant figures, so we go back to the beginning. This has 3. This has 3. This has 3. So our answer we're going to present in 3 significant figures. And we're going to say that work is equal to 267,000 joules. We can do 267,000 joules of work. Okay. Is that okay? Doing something different, calculating work while doing the exact same thing. You gotta love it. That's efficiency right there. while no engine may be able to be 100% efficient, but our calculations are. They're beautiful. Beautiful. Okay. No questions on that one? All right. So let's do this one. How much work can be done by a 3.50 kilogram pool of water that increases 56.5 degrees Celsius if the specific heat of water is 4.184 joules per grams degrees Celsius? All right. Can I erase this? Anybody still writing this? Okay. Selective erasing. What are we given? We're given the mass, and it happens to be the exact same mass, yes? Instead of a 3.50 kilogram piece of metal, it's a 3.50 kilogram pool of water. It increases the same amount as our piece of metal did by a factor of 56.5 degrees Celsius. The only difference is we have a different specific heat. The specific heat of water is 4.184 joules per grams degrees Celsius. Now, just a heads up, if you start looking up problems like this, sometimes it'll give you your specific heat in calories per grams degrees Celsius. So just pay attention to whether this is a J or it says calories, C-A-L. All right? Because then your numbers are going to be a little bit different. So you may look it up and you're like, hey, this says the specific heat of water is 1, not 4.184. That's because it is. It's 1 calorie per gram degree Celsius, but 4.184 joules. All right. So we still are given mass, specific heat, and a change in temperature. Right? And so we're still going to use the same tool, and we still want to find the same value. How much work can be done? And so work is equal to 3,500 grams times our new specific heat, which is 4.184 joules per grams degrees Celsius, times the same temperature, 56.5 degrees Celsius. Degrees Celsius is divided away here, multiplied here, so it cancels out. Grams are divided away here, multiplied here, so they cancel out. And we are left with 3,500 times 4.184 times 56.5. How many significant figures should we present our answer in? Still 3? Remember, we're not going to limit it to 2 here because this was actually given to us as 3 significant figures. So we're going to present our answer in 3 significant figures, and it is 827,000 joules. What was the answer to our other one? Was it 267,000? 267,000. This is 827,000. So almost 4 times as much. Really just actually a little bit more than 3 times as much work that can be done. Same amount of material, same temperature change, but a much higher specific heat. And so let's think about this. If you were going to design a machine and you needed to keep it cool, what would you use to keep it cool? Yeah.
Water.
Why?
Because it can absorb more heat.
Yeah, you would absolutely use water, and it's because water has the highest specific heat. So it can absorb more heat while changing temperature less. Yeah, Josh?
That would be why in World War I they had lots of water jackets for their weapons.
Yep. And that's why cars use water to cool the engine. You've got a radiator which has water cycling through lines to keep the engine cool. And why you have water running through all of the machinery in nuclear power plants, keeping them from overheating. And That's why you have a lot of nuclear power plants built along either major rivers or where you have a major lake or on an ocean, so you can cycle water through your plant to keep things cool. Now, if you were going to design a machine where you wanted to, dump energy into something to store it, right? Not necessarily to use a material to keep your system cool, but if you wanted the ability to store energy, what material would you use, do you think, to store energy in? You would still use water. And that's because water, again, acts as like a heat sink. You can dump enormous amounts of energy into it without getting, wild changes in temperature. And so water is a really, really nice material. And you see water at play basically in all power plants, not just hydroelectric power plants. Hydroelectric power plants usually take running water, like you'll set up a dam, and then you have a hydroelectric power plant as water moves from now the reservoir behind it, the man-made lake, through, and trickles out and turns some kind of a turbine to generate electricity. But even in nuclear power plants, you have a lot of that nuclear energy harnessed by the breakdown of nuclear material. It actually gets put into water that is then used to turn some kind of a turbine and generate electricity. And so water plays an integral role in keeping things cool and also acting as a great sink to just store a bunch of energy. All right? Now, these problems could be set up in such a way that you had to solve for a different variable. Okay? In all of your homework problems, they're set up like this, where you're either calculating heat energy for Q or you're calculating work, but you're using this tool. So they're all set up that way. But if what I want to show you is just algebraically how you can manipulate this tool to be able to solve for any piece that you might be asked to do in the future. All right? So here's our tool here. Work is equal to mass times specific heat times the change in temperature. But let's say we wanted to solve for mass. How would we solve for mass? Right now you have specific heat and change in temperature being multiplied to mass. How do we do away with something that's being multiplied to it? We divide it. So we would divide both sides by C delta T. And we would have that mass is equal to work divided by C, specific heat, times change in temperature. All right? If we wanted to solve for specific heat, and we have mass and change in temperature being multiplied to specific heat, how would we get those away? Yeah, we divide by it. So then specific heat would equal work divided by mass times change in temperature. And then finally, if we wanted to solve for change in temperature, and we have mass and specific heat being multiplied to change in temperature, how do we get away with something being multiplied to it? We divide it away, and so we would end up with change in temperature is equal to work divided by mass times specific heat. And so there you have a way, an algebraic manipulation of our tool to solve for any of these variables you may be asked to find. Remember that Q in our setup, we're saying Q is equal to W, which means any of these tools could be Q divided by C delta T, Q divided by M delta T, Q divided by MC. All right? Is that okay? All right, so again, all of your homework problems, you're asked to just do a straightforward use of the tool as given.